So what we ended up with in the last video was a description of how the thermal energy density changes in time at a point along the rod. Okay? And so to kind of bring it back up, so here's our rod. Our coordinate system was over here, x is 0, x is equal to L. And the differential equation, partial differential equation we came up with was, how does the thermal energy density change in time? Well, that's going to be minus the partial derivative of the flux in space plus whatever source term we have, whatever energy is just spontaneously generated. Okay? And so, as I said before, our goal is going to be to, instead of using a thermal energy density, use something that we're a little more comfortable with. So the goal now is express the same equation in terms of temperature. And what notion or what notation are we going to use for temperature? Well, that's going to be U of x comma t. Okay. So to make this conversion, okay, first question we should ask is, well, how do thermal energy temperature, and in the end, as well, the thermal flux, that term phi. So how do thermal energy, temperature, and thermal flux, how do all these quantities relate? Right. Okay. So what we're going to start with is relating thermal energy and temperature together. And after we have that, then we're going to revisit this thermal flux. Okay. So for thermal energy to temperature, we're going to need another concept called specific heat. Okay. And we're going to give it a name C of x. Okay. So what is specific heat? Well, specific heat is the heat energy required to raise, okay, heat energy required to raise the temperature of a mass of a substance. So this is a property of the material. Okay, different materials require different temperatures to raise the temperature, or different amounts of heat to raise the temperature. Solids, as an initial example, solids require different amounts of energy than liquids might, just because of properties of the materials. Okay. And so a comment in the book makes this comment that in practice, specific heat is actually a temperature of both the material, or is a function of both the material and the temperature in question. Right. So if you have the material at a higher temperature, you may need less energy to raise it one more degree, just because things are already moving, etc. But here, but we'll assume that C only depends on space and not the actual temperature. Okay? And what may help is, well, what are the units of C? Okay, so C as units. So joules, so energy per mass times temperature. Okay. So if we want to end up with joules when we're using specific heat, we need to multiply by mass. We need to multiply by kind of the temperature. Okay, and so in the end, that's how temperature is going to appear. Okay, but here we're incorporating mass. Okay, previously we just incorporated volume. Well, how do we connect the two? So since we're using mass, we need to introduce kind of mass density. Okay. I'll write it in green here. And usually we're going to denote by, so for mass density, we're going to use the function rho. It's in LaTeX, it's \rho, whatever. It's a Greek letter, just means density. This is mass per unit volume, right? And so the units are mass per, say, meter cubed or what have you. Okay. Okay, so we have all the pieces we need. So recall that if we take this thermal energy density, E of xt, multiply it by the area A, delta x. Okay. Joules per volume, we end up with joules, our energy. Okay. So what else? So if instead we start with this specific heat, C of x, okay, remember that C of x had units joules per mass times temperature. Okay. So for mass, here, let me draw a picture. So if we have a thin slice right there, okay, so this has area A, this distance is delta x, and we have a notion of density, right? How much mass per volume, okay? So assuming that the mass density is constant in this small region, the total volume here is going to be mass density times volume. Okay, that's going to give us the total mass. So specific heat has units joules per mass. Okay, so if we want to get rid of that mass in the denominator, we need to multiply by rho of x density times volume. Okay, it also has temperature in the denominator, and so we're going to multiply by the temperature of our material in space and time. We do the dimensionality reduction or dimensionality analysis. Things cancel and we're left with joules. Okay. So how do all these quantities relate? Well, thermal energy density times volume that in the end turns out to be whatever the specific heat is times mass density. I'm going to bring temperature over here times temperature times volume. Okay. And of course, we have common terms. Divide by A delta X. And we end up with thermal energy density equal to specific heat times mass density times temperature. Cool. And so, so this is great. Okay. Now what we can do is go back up to our original differential equation relating thermal energy density to flux and source. Okay. If I paste that right here, make this bigger. Why not? Okay. So now what we can do is instead of that E of xt term, we have this, I shouldn't have done it like this, but okay. I'm going to do it. Okay. So minus derivative of the flux plus the source. So, right, E of xt used to be right there. So what we're going to do is we're going to substitute in this new expression for E of xt. It's going to be C of x, rho of x, U of xt. Okay, and that's going to be minus the partial derivative of flux plus the source term. Okay. Notice that here, specific heat and density don't depend on time. Properties of the material, the properties of the material isn't changing, just the heat, okay, or the thermal energy. So we can pull those out. And end up with this expression here. And that's minus the flux, and I can write out the arguments as well, plus the source term. Okay. Okay. So we're almost there, almost have the heat equation as we'd like it to be. But this is good, right? So it tells us how, right, how the temperature is going to change depending on properties of the material and how the heat flows, as well as whatever energy is created or pulled out of the system at any specific point along the rod, at any specific point in time. Cool. And so then the last piece that we need to deal with is this flux term. Okay, can we relate flux back to temperature? Okay, so written out. Question: can we relate flux to temperature? The good news is that yes, we can. Okay, so how do we do that? So these are these things called Fouriers laws, maybe of heat conduction. And how these work is, well, we're going to give a set of observations, okay? And then we're going to quantify those observations. Okay? So what are the observations? Well, one, temperature. If your temperature is constant in a region, then no heat energy flows, or no temperature flows. no heat energy flows. Okay, there's no reason for heat to change, then it's not going to change. True. So if there's a difference in temperatures, so if there are temperature differences, then energy flows from hot to cold. Or if you have something hot, it's going to cool down. If you have something cool and kind of the environment that it's in is warmer, heat's going to flow from the warmer thing into the cooler thing and warm the cooler thing up. 3, so the greater the temperature difference, greater the temperature difference, greater the flow of energy. Okay, and then finally 4, flow will vary. So the flow will vary for different temperatures. Sorry. Okay. Flow will vary for different materials. Even with the same temperature. Okay. Right, so maybe a liquid and a solid, right? They're at the same temperature. One might lose their heat faster than the other. Okay. So these are just some observations about how things behave. Hopefully it appeals to your intuition about how the world works. But what we'd really like to do is quantify all this stuff. Okay. And so the way we're going to do that is via this law. Okay. So all of this is talking about how heat flows, right? Heat flows via flux. Flux is how energy moves. Okay. So what this is saying is that the flux is going to be minus some function k0 of x times d dx u of xt. Okay. So where are all these pieces coming from? Well, energy is flowing from hot to cold. Okay. So 2 right here, energy flows from hot to cold. That's going to give us this minus sign. Okay. Flow will vary for different materials, even with the same temperature differences. So 4 right here. That's where this constant or this function, say, this property of the material, that's where that comes in. Finally, greater the temperature difference, greater the flow of energy. Okay, that's telling us that the flow should depend on the gradient of the temperature, right? That temperature difference. So 3 right here. U of xt. Okay. Okay. And so this is called, usually called Fourier's law, law of heat conduction. Okay. Cool. Okay. So what we've gained here is we've related flux to right? Properties of the material as well as properties of the temperature. Right, so if we bring back, so let me copy all of this. So if we take this, copy, move it down here. So what changed? Well, we've described the flux in terms of material and temperature. So I'm going to erase all this. Remember, we had a minus sign in front. X derivative of the flux is going in here. What is the flux now? Well, that's minus K0 of X d dx u of xt, okay, plus that source term. So we can make one simplifying assumption, right? Notice we have a minus and a minus here. Derivatives, you can pull scalars out, you can pull signs out. And so I'll write this without the arguments. Du dt is equal to d dx k0 du dx plus q. Okay, and this was our goal all along. This is the heat equation, which tells us how temperature flows, how temperature changes through time, depending on the materials of the object. Okay. So two quick observations. Right. So if the specific heat, the mass density, and this function K0, which told us kind of the flow rate depending on the material. Okay. So if the rod is made of a uniform material, high quality, whatever. So if all of these quantities are constant, okay, notice that now, so K0 is a constant, so K0 can be pulled out. Okay, these are both constants. Presumably they're not zero. Okay. Then what we can do is, so du dt is equal to, and I'll write it like this, K0 over C rho. Remember now, this is all a constant, times du dx of, or d dx of du dx plus q. And we can simplify this a little more. So all of this stuff, we're just going to treat as one constant depending on the material, times a second derivative, temperature, plus whatever Q is. And so then, of course, if Q is zero, right, if there's no source, or if heat's not generated or spontaneously lost, then we end up with, right, our I don't know, goal of the goal, as written before, d squared u dx squared. Okay. Okay. Cool. So one comment that I'll revisit in later sections a lot more, and is another main piece of this course and working with PDEs and differential equations in general, is notion of initial condition, right? We're saying here's how heat is flowing, okay, through time. So I'll write it like this. If we say heat flows like this, okay, we should ask, how did it start? So it's how did it start? This is the initial condition, right? And you've seen initial conditions before in working with ordinary differential equations. In practice, how this works is, well, let's say, so for du dt is k d squared u dx squared. Okay, so for this equation, also need to know u at time 0, the initial temperature. Okay. And that we'll just say is some function f of x. Okay. For a lot of the exercises, we'll keep f of x general. We'll just keep it as some arbitrary initial condition. Sometimes we'll specify an initial condition and we can actually solve exactly. Yeah. And so one other feature of PDEs is that, so it turns out we also need values, let's say, values for the temperature at the endpoints. Okay, so in this case, turns out it's not enough to just give that initial profile. We also need to specify something about how this temperature is behaving at the endpoints. And so for this rod, we need to specify, i.e. we need u at 0t and u at L of t. Okay. And there are a lot of other aspects. Okay. Initial conditions and boundary values. Boundary values are two other key components of this course that we'll touch on a lot more in coming lectures. So stay tuned.